All right, guys. In this video, we're going to look at an AP Physics 2 free response question from Unit 4 dealing with electric circuits. And this is a long free response question, so the suggested time to be able to complete a question like this is about 25 minutes. So they give us two circuits here. It says, the two circuits shown above contain an ideal variable power supply, right there, an ohmic resistor of resistance R, an ammeter A, and two voltmeters, VPS and VPR. So this is the voltage across this resistor, and this is the voltmeter across the battery, the power supply. That's what PS stands for. In circuit 1, the ammeter has negligible resistance right here. This is circuit 1, so it's just an ammeter, and it's ideal so that it basically it acts like an ideal wire, so it's basically, you can pretend that it's not in the circuit. It doesn't affect the circuit. The voltage across this wire is ideal. There's no voltage drop across it. And in circuit 2, the ammeter has significant internal resistance, or significant internal ohmic resistance R. So kind of think about it like a non-ideal battery, right? So we've got our, just think little like a dashed line around there, and in this meter itself, there's some small internal resistance. It's significant enough we have to factor it in, some resistance lowercase r. The potential difference of the power supply is varied, and measurements of current and potential difference are recorded. A says, the axes below can be used to graph the current measured by the ammeter as a function of the potential difference measured across the power supply. On the axes, do the following. Sketch a possible graph for circuit 1 and label it 1, and sketch a possible graph for circuit 2 and label it 2. Well, this is just as simple of a circuit as it gets. You vary the voltage of the power supply, that varies the voltage across the resistor, which is going to vary the current that goes through it. And it says this is an ohmic resistor. And remember, what does an ohmic resistor mean? Well, when resistors are ohmic, if you vary the current through something and the voltage across it, when you graph current versus the voltage across it, or vice versa, you're going to get a linear relationship. So whatever we draw for the relationship between current and potential difference across the resistor, which is the same as the potential difference across the power supply, like you're going to get a linear relationship. But how does it look different if we have that added resistance from the ammeter right here? Well, with this added resistance, we now have two resistors in series. This added resistance from the ammeter is going to increase the overall resistance of this circuit. Okay, so bigger overall resistance for circuit 2, then for circuit 1 for the same setting on the power supply. So circuit 2 has a larger equivalent resistance with the internal resistance of the ammeter in series with resistor R, like we just talked about. And Ohm's law, well, this equation right here works for only for ohmic resistors, and in this case, both resistors, big R or little r, are ohmic. So how do we think about how this translates to like the shape of a graph or what's going on in the graph? Well, notice we have current on the y-axis and power supply potential difference, or delta V, on the x-axis. And so let's rearrange this equation to put it in the form of a line, because that's what we're expecting for ohmic resistors, where I is in place of y and delta V is in place of x, right? That's what's graphed right here. So if we kind of like pull delta V out to the side, like we just rearrange a little bit, we get I equals 1 over R times delta V, right? That's just this, just a little, looks a little bit different. But notice, doing that, we now have this equation in the form of a line. Y equals the slope, or m, times x plus the y-intercept, and we can see, you know, I's on the y-axis, that's what we wanted, that's our current. Change in electric potential by the power supply, that's on the x-axis, that's what we got down here. And notice, whatever is multiplied by x, which is delta V, is the slope. So the slope in a graph like this is the inverse of the resistance of the whole circuit. And so, like, how will so apparently, if this circuit has a larger resistance, it's going to have a different slope on the graph than circuit number 1. So we said circuit 2 has a larger equivalent resistance. So if circuit 2 has a bigger R total, like R value, and I'm going to Let's say that R EQ to remind us that's the equivalent resistance right here, which is R, big R plus little r for circuit 2. So that means if this value is larger, the slope, which is 1 over a bigger value, will be smaller. So as the equivalent resistance is bigger, the slope will be smaller. So the slope for the graph of current versus power supply potential difference will have a smaller slope than that for circuit 1. Like how much smaller though, totally depends on how much added resistance that ammeter adds to our circuit. All right, part B says let delta VPS be the potential difference measured by voltmeter PS, so the power supply potential difference, across the power supply, and let I be the current measured by the ammeter A. For each circuit, write an equation that satisfies conservation of energy in terms of delta VPS, I, capital R, and little r as appropriate. Let me get our diagrams up here to talk about. So here's our two circuits. And first of all, we need to ask, like, what does it mean for an equation that satisfies the conservation of energy? Well, remember, in a circuit, the voltage at different points, or the change in voltage across something, tells you how much voltage is joules per coulomb, how much joules of energy are stored per coulomb of charge. And so Kirchhoff's loop rule is kind of like an energy conservation equation. Remember, it's the sum of all the changes in voltage in a loop must be 0. Why? Because if we add up all the changes in energy from one position to another position, that's got to be equal to 0, because the energy of a charge, let's say at the negative side of a battery, by the time you increase voltage and increase energy, and then you decrease voltage and decrease energy, you have to basically come back to the same energy you started with right there for energy to be conserved. So when it says write an equation that satisfies conservation of energy, it's asking you to write an equation using Kirchhoff's loop rule, where the sum of the changes in electric potential, or the changes in voltage, add those things up for any given loop, must be 0. So let's do that for circuit number 1. If we start on the negative side of a battery, the first thing that's going to change our voltage is the battery. So it goes up by delta VPS. Then we're going to add to that the change in voltage across just this resistor R, delta VR, and that just goes to 0. And remember that the voltage is going to increase across the battery and decrease across the resistor R. And we can't use delta VR, so we need to substitute in an expression which tells us how much the voltage is going to change. And I know we've done this stuff a lot, but how do we know what the voltage drop is across anything? Well, we kind of have to go back to our Ohm's law from AP Physics 2 equation sheet. If we rearrange that for delta V, we get that the change in voltage across anything is equal to the current through it multiplied by its resistance. So if we wanted the change in voltage across big resistor R, that's equal to the current through it times its resistance. I stands for the current through, well, not only battery, but also through resistor R, so it's just capital I times capital R. And here's our equation. That's our equation for that satisfies conservation of energy. How does that change for the second circuit? Well, if we look at the second circuit, and we also start at the negative side of the battery, the voltage is going to change when you go across the power supply. It's going to change when you go across little resistor R. So we got delta V, little case r, lowercase r. And it's going to change when we go across the big R right there, so delta VR. We add up the changes in voltage across the battery, the internal resistor, and the external resistor. The sum of those things has to equal 0. And using Ohm's law again, an expression that's the same as the change in voltage across a little resistor is the current through it, I, times its little resistance. And the voltage will drop again when it goes across resistor R, equivalent to the current through it times its resistance, so minus I times capital R. And this expression, when you add up all three of those terms, that has to be equal to 0. So here's the equation that satisfies conservation of energy for circuit 2. Part C says, explain how your equations in Part B account for any differences between graphs 1 and graph 2. Well, remember, here's our graphs for graph 1 and graph 2. We said that graph for circuit number 1 had a steeper slope than the graph for circuit 2. So how do these equations that we just derived and developed explain or show those differences? So when we take this equation right here and we solve it for, let's say, if I solve for the change in voltage across the power supply, right? I'm going to add IR to each side, so it moves it over here, and we get the change in voltage across the power supply is equal to the current coming out of the battery times the big resistor. Or if we solve that for I, we get something that looks like Ohm's law. I1 equals delta VPS, the voltage difference across the power supply, divided by our resistor R. So for any given voltage at the power supply, they will give us what I1 is, the current coming out of the battery. Well, if we do that using this equation for circuit number 2, notice if I solve for change in voltage at the power supply, I'm going to add negative I little r, and I'm going to add I times little r, and I'm going to add I times capital R to the left side and the right side. So it moves it over to the right side. And if I factor out I, because that's the same, there's the same current going through the little resistor as there is going through the big resistor. So we get I times little r plus capital R. So we get that the change in voltage from the power supply is equal to current times little r plus big R. Or if we solve that for I2, we get I2 is equal to the change in voltage across the power supply divided by little r plus r, which will be bigger than just r, right? Because we're adding something to it. So from these equations, we can now explain the differences in the graph. So as seen from the equation on the left, for a given voltage provided by the power supply, I2 will be smaller because of the increased total resistance. Remember, R plus R, little r plus big R. This leads to a smaller slope in part A for circuit 2. Because if we just plug in any change in voltage across the power supply here or here, we can see that because down here we're dividing by a larger number, for any x value, delta PS, delta VPS, we're going to get a smaller current value. And so if we go back to our equations, right, say for a given voltage power supply, we're going to get a smaller value for I2 than we are for I1. And that's the case anywhere we check. For this larger voltage delta VPS, we get a smaller I2 than I1. So that explains the differences in the graphs. Part D reads, in circuit 2, big R is 40 ohms. It says when the voltmeter VPS reads 3 volts, so that's the setting of the power supply, the voltmeter VR reads 2.5 volts. It says calculate the internal resistance little r of the ammeter. So remember, this is the voltage of the power supply, so I drew the circuit right here. So they're saying when this variable power supply is set to 3 volts, the voltage across R, which they're saying is 40 ohms, is 2.5 volts. And it wants us to calculate the internal resistance of the ammeter, that little r. So what is R right there? Well, if we go back to Ohm's law and use this thing works for, any individual circuit element. And so the current going through the little resistor is equal to the change in voltage across that little resistor divided by, well, the resistance of that resistor. So if we can, that little guy right there, R, we're solving for that. We can figure out little r, or the resistance of the little resistor, if we can figure out the voltage across it, and we can figure out the current going through it. So let's jump back over here. The voltage has to go up by 3 volts when it goes from the negative side to the positive side of the battery. It's got to drop by some amount and then drop by the remaining amount to get back to 0 volts. So if there's a 2.5 volt drop across the 40 ohm resistor, that means there has to be like the difference between these two values across little r. So because if it goes up by 3 volts, if it goes down by 0.5 volt and down by another 2.5 volts, it's going to make it all the way back down to 0 volts. So if there's a 2.5 volt drop across the 40 ohm, there must be a half volt drop across little r. So delta VR is 0.5 volts. But in order to solve for the resistance, which the problem is asking us to do, we have to first figure out the current going through the resistor. So what is I, right? There's current coming out of the battery. It all goes through R, little r, and it all goes through big R like this. And so if we have a simple series circuit, how do we figure out the current going through that? Well, Ohm's law also works for like equivalent things. So like the current coming out of the battery is equal to the voltage across the whole circuit divided by the equivalent resistance of that circuit. So the current, or we can just go back and use this for the 40 ohm resistor. So the current going through the 40 ohm resistor, which is the same as the current going through the little resistor, which is what we're looking for, is equal to change in voltage across it divided by its resistance. And it told us there's 2.5 volts across that 40 ohm, and it has a resistance of 40 ohms. So 2.5 volts divided by 40 ohms gives us a current of 0.0625 amps. So if there's 0.0625 amps going through the 40 ohm resistor, it must also mean there's 0.0625 amps going through that little resistor. So we can just plug that in for I sub little r, and we can solve for that resistance. A couple steps of algebra, and we get that little r is equal to the voltage across it divided by the current going through it. So 0.5 volts divided by 0.0625 amps gives us finally that resistance, which remember they said is not it's significant. It's not negligible. Is about 8 ohms. Moving on, part E, it says voltmeter VR in circuit 2, so the voltmeter that was across the 40 ohm one is replaced by a resistor with resistance of 120 ohms to create circuit 3 shown below. It says the voltmeter across the power supply still reads 3 volts, so that's still providing 3 volts. Here's our ammeter with significant resistance. Remember we said that's 8 ohms, but now we've just added, instead of a voltmeter, another 120 ohm resistor. Part 1 asks us to calculate the equivalent resistance of the circuit. So we have an 8 ohm, that's little r, that's what we just found in the last part, in series with a 40 ohm and 120 ohm in parallel. So we just draw a simple slide circuit. Since these two things are in parallel, you can find the equivalent parallel resistance of both of those using the parallel resistance equation. And you get that the equivalent parallel resistance of a 40 ohm and 120 ohm resistor is just 30 ohms. And so you can redraw these two guys in parallel as one equivalent resistance. So you could just it's behaving just like a single 30 ohm resistor. So now we have one simplified step in an 8 ohm resistor now in series with a 30 ohm resistor. And then remember to combine series resistors, you just add those two things together. So an 8 ohm and a 30 ohm in series act like just one 38 ohm resistor. And so the equivalent resistance of these three turns out to be 38 ohms. The last part, part 2, says to calculate the current in each of the resistors that are in parallel. So we go back to not our simplified form here, right? Well, we know what that this is. We'll have to use that in just a minute, but we want to know, it's asking us to calculate the current going through the 40 ohm and the current going through the 120 ohm. Well, again, this is an Ohm's law question ultimately. So current going through something through the 40 ohm is equal to the voltage drop across the 40 ohm divided by its resistance. And the current going through the 120 ohm is equal to the change in voltage across it divided by its resistance. So how do we know what the voltage drop is across these? Because that's not given. Well, we know that there's going to be current that flows out of the battery, and that voltage, well, the current will go all through the 8 ohm. So as current flows through the 8 ohm resistor, little r, the voltage is going to drop. It starts at 0 at the negative side, the battery ups it to 3 volts, and the voltage will drop by some amount when it gets here. Well, if we can figure out what the voltage is on the other side of the 8 ohm resistor, we can see that the voltage has to go from whatever that value is all the way down to 0 across each of those resistors in parallel. So we first need to figure out what's the change in voltage across that 8 ohm resistor. Well, to do that, we need to know the current going through it times its resistance. So how much current flows through that little 8 ohm resistor? Well, that's the total current that comes out of the battery has to go through that 8 ohm resistor. So we have to use Ohm's law first to figure out the current coming out of the power supply. That's equal to the change in voltage across the power supply, or the change in voltage across all those resistors. That's the same thing as the voltage power supply, which is 3 volts, divided by the equivalent resistance of these guys. So if there's, let's say, 3 volts across all those resistors and they act like a 38 ohm resistor, you take 3 volts divided by the equivalent resistance of 38 ohms, we get that there's 0.079 amps of current flowing out of the battery, which also flow through this little resistor. So let's use that to help us figure out what the voltage drop is across that little resistor. So the voltage drop across the 8 ohm is equal to IR, the current going through it, times its resistance. So there's 0.079 amps going through it. It's got a resistance of 8 ohms, and an ohm is the same thing as a volt per amp. So you can see that the amps cancel, and we get that there must be a voltage drop, or there must be a change in voltage across that resistor of 0.632 volts. And since we're going from left to right and current is flowing from left to right, the voltage that starts at 3 volts has to change by 0.632 volts and has to go down. So what's 0.632 volts lower than 3? That's 2.37 volts. So once the voltage drops, the voltage on the right side of the resistor or anywhere along these ideal wires, right? Voltage doesn't change unless you go across a resistor. Doesn't matter if you go through through a junction, the voltage will stay the same. So there's 2.37 volts here and here. So that means there's 2.37 volt potential difference across each of these resistors. So now we can calculate the current through each of them. So across the 40 ohm, there's 2.37 volts divided by its resistance. We get the current going through it, 0.06 amps. And for the 120 ohm resistor, there's also 2.37 volts across it. They're both in parallel, so they have to have the same voltage drop across them. But if we have a larger resistance, 3 times larger, the current will be 3 times smaller. So the current going through that one will be 0.02 amps.